Everyone. It's my great pleasure to make this presentation today. My name is Huashen Xie, a master's student from National Sun Yat-sen University in Taiwan. So the title of my study is the Electrolyte molecule absorption behaviors and the capacitance of supercapacitors with nanoporous carbon electrodes, a coarse-grained molecular dynamics study. This is the outline of my presentation. So first, I will introduce the motivation and background of my study, and then the simulation method and the module will show in this part. And I will discuss the simulation results in detail and finally make some conclusion for my work. The electronic device has become important in human life, such from portable small device to big electric vehicle. In those electronic devices, the energy storage problem is always the limitation and the crucial issue. So for the energy storage technology, the batteries and the capacitor are the most commonly poured source in commercial market, especially in lithium battery and the electric double-level capacitor, EDLC. In general, lithium battery can release and storage through the chemical reactions and obtain the high energy density, but the electrochemical corrosion causes electrodes breakdown. It reduces the cycle life and has safety concern. But oppositely, EDLC is storage through the purely physical reaction. Although the energy density is lower than battery, but its high reliability, cycle life, and the discharging in high rates also catch people's attention. So such EDLC device is the topic of my study. Here shows 6 typical types of carbon electrodes for the EDLC device. So in our previous work, we have used graphene as electrodes and different concentration of organic solution as electrolytes to investigate the diffusion number and the capacitance. So compared with the graphene electrode, the activated carbon electrodes offer more higher surface area and volumetric capacitance. In the experimental method, it is difficult to directly observe the ion absorption inside the electrodes. So in this study, we use the MD, molecular dynamic simulation, to investigate the ion absorption behavior and the capacitance of electrolytes in the different densities of AC electrode. In our previous work, we have successfully predict the structure of AC by combining the timestamp for BIOS Monte Carlo method and the simulated annealing method. So we use the same method to construct the EDLC module for this study. The structural properties of those models are shown in this table. Including the average pore size and porosity and the surface area. In order to reduce the numerical calculation time for the large number of systems, the electrolyte has been coarse-grained. So in this slide, we show the all molecular structure in OH model and the coarse-grained model. So we use the optimized potential for liquid simulation 0810 for to discredit the interactions between the atoms in the 0810 model, which was proven as good molecular described to the organic liquids in the previous work. So we use the OPLS-A8 as a force field to generate the reference data and then revert to the multi-scale coarse-grained method, which developed by the fourth group, which is describing to derive coarse-grained force field for the molecular liquid from the atomistic scale forces. And we get the CG parameter through this method. So after we obtain the CG parameter, we found this procedure to get the EDLC module. First, we place the electrolyte molecules between the symmetric AC electrode. Then second, the system was annealed from 800K to 300K by MD simulation in the MVTs assembled during 5 nanoseconds. Then third, the length of box in this direction is adjusted and makes the density of box region matching experimental value. And finally, the electrodes have been charged by the constant potential method under a voltage electric potential at least 5 nanoseconds until the system reaches equilibrium. Now research and discussion. Figure ABC shows the average number density in the density 0.8 AC under 0 voltage electric potential. So in figure A, the solvent has the ions are distribution evenly, but we can find that the lower density of AC electrode have commanded more ions compared with 1.2 case in AC electrodes. So the purpose of our research is to investigate the ion absorption condition in the AC electrodes. So we have the density 1.2 case have been excluded in the following analysis. These two figures shows the average number density of ions under the 2 voltage electric potential. So we can see that the ions are attracted to the electrodes due to the strong Coulomb interaction, and there is no much number exchange as the electrode interface. In order to understand the local structure inside the electrodes, so we analyze the various absorption modes of ions inside in the AC electrode surface, and with the degree of confinement. According to the previous work by Merlet, the value of DOC can define in 4 different parts: edge, plane, hollow, and pocket. So in figure A, the DOC of electrolyte molecules in density 0.8 AC under the 0 voltage electric potential. The solvent has a better amount of distribution than ions. That's made due to the smaller size and the good velocity in the of the solvent molecule. And figure and see the cations and anions are shown in the density 0.8 AC at 0 voltage and 2 voltage electric potential. So in the cathode, the cation have the high distribution at the plane part, and but still minimally distributed in the edge parts. That's due to the large size of cation. But in addition, the anion have the DOC of anions have approached to 30%. That's due to the smaller size easily to diffuse into the electrodes. These two figures shows the DOC of ions in the 1.0 AC electrodes. The ion distribution have the similar pattern in the with the case of the density 0.8 AC. So we can find that the higher density AC electrodes cannot easily to diffuse by ions. Finally, the capacitance are listed in this table. In the different density of AC carbon electrode and with the graphene electrodes published by the in our previous work. So the total capacitance is calculations from corresponding integral capacitance at cathode and anode in under the 2 volt electric potential by this equation. So we can find that compare the capacitance with the AC electrodes. The lower the 0.8 AC electrode have higher capacitance. That's due to the lower density of AC electrodes can give more space for ion absorption. And finally, we compare AC electrode and the graphene electrodes. Due to the AC electrode has higher specific surface area, so AC electrode have more capacitance than the graphene electrodes. Finally, we make some conclusion from my work. The ions are difficult to diffuse into electrode when the density of AC electrodes higher than the density 1.0. The result of average number density indicates that no obvious ion exchange at interface of electrodes. The results of the graph of confinement show that anions are easily to diffuse into electrodes due to their small size, but cations are mainly distributed at the edge part of electrodes. The EDLC module with density 0.8 AC electrodes show higher capacitance than the case with density 1.0 and the graphene electrode, which theoretically store more about 26% and 50% of charge than the other two cases respectively. This photo show our lab members, and finally we thank the National Science and University and the Ministry of Science and Technology of Taiwan. Thank you very much for your attention.
Okay, now for questions. Yep. It's a very interesting results, but I have a question regarding the modeling, because in your three cases you used I think low surface area carbons, because usually even commercial carbons can have like up to 1,500 square meters per gram. Have you investigated the activated carbon, the modeling of activated carbons with such high surface area? Because here in your work you had around from 500 to 700 square meters per gram. What happens if the surface area is like twice higher?
We calculate the surface through the types of package. Yes, it is post-orbital. Yes, this can shows the module in the we did directly invest the surface area through this package. So yeah, so we can compare the surface area between different density of AC electron.
Okay, but have you investigated what happens if it's higher than what you have shown us? Like, what is the results are like? Is the capacitance is actually greater if it's like 1,500 square meters per gram, or have you not investigated it yet? Well, if not, then I'll ask them like that.
Okay. So, any more questions? Oh, if not more, so very good. So now I'll close to.